Let's take a look at the periodic table. Hydrogen is kind of in an unusual position because it could either lose one or gain one. If it loses one, we form the hydrogen ion. If it gains one, we form the hydride ion. Mostly the elements on the left side of the periodic table lose or gain electrons. Yeah, they lose. Hydrogen's weird. So we can do some periodic tables will write in two positions, like this periodic table here. This is the periodic table that you'd get during a test, let's say. Here, I'll pass this out. Normally what you do is we pass it out for the test and then collect them at the end. And you can use this for today's.
Hydrate is right? Yeah, but that's negative charge. It doesn't mean
that's exactly. Oh, it's gaining an electron because it's a negative charge. I have my.
I don't think the minus sign stands for like.
I got some A on that site that I was worried about last week.
So if you look at hydrogen, hydrogen's a member of two families. It's a member of the alkali metals, even though it's not a metal. It does have some characteristic properties of the alkali metals. That is, it can lose one electron, like the other alkali metals. And it's also a member of the halogens. Do you see that? Group 7B. One thing I don't like about this periodic table is I like it where it goes beryllium. Do you see element number 4? That's 2A. And then when it goes to scandium, element number 21 there, I like it to go 3B. And then have those as the Bs. And then at boron, it would go 3A there. So I'd have the A separated into two blocks. Okay. But the other members of the alkali metals family will form +1 cation. So we have Li+. Li+ is called what? Lithium. If we just call it lithium, then we might get it confused with lithium metal. Lithium metal has no charge, so what we have to do is we call this the lithium ion. If you want to be more specific, it'd be called the cation, C-A-T-I-O-N. Cation. Cations are positively charged anions. A-N-I-O-N would be negatively charged. So we have lithium ion. What's below lithium? Sodium. And it would also form +1. This would be the sodium ion. Is lithium, actually hydrogen is pretty tiny. So if we're looking at H+, lithium is a lot bigger. What about sodium? Would it be bigger, do you think, or smaller than? Bigger? Yeah. Bigger, it would be bigger. And then from sodium we would go to potassium. And so we'd have potassium ion. Potassium ion is 1T or 2T?
1T.
How many S's?
2.
Yeah. Potassium ion. It's even bigger. Then after potassium, Rb, which is rubidium. And then let me squeeze it down here. What's underneath rubidium?
C6.
Cesium. That's also less charged there. Cesium would be the biggest of these.
Do we still call those ions? Or
What's that?
do we call like the rubidium ion?
Yeah. You'd have to call it ion, otherwise you might confuse it with the metal. And the metal and the ion behave significantly different.
And that last one is cesium?
The last one's cesium. There's two ways to spell cesium. We use the American English version. The American English version is Cesium. That would be it. The other version will have an A stuck in there. CEA.
Oh.
Did you say that the hydride version of hydrogen is what it gains electrons?
Yeah, when it loses an electron, it shrinks down. You know, when it gains an electron, it blows up. Maybe this is over exaggerated, but it's kind of what you expect. And so one of the chemical properties of the alkali metals is they tend to lose an electron to form a +1 cation. This +1 ion. These would be the names of the ions. These would be all what we call fixed charge ions. Okay, next to lithium is what? In the same row, not in the same family. This family would be the column, but in the same row as lithium would be beryllium. And beryllium ion would have what charge? Yeah. Beryllium is very toxic. We're not going to worry too much about beryllium. Underneath beryllium, we have magnesium. Now, if we compare lithium to beryllium, what do you think is bigger? Lithium or beryllium?
Lithium.
Lithium's bigger, beryllium's smaller. That's correct. So beryllium's got 2 plus, and it's smaller. Now, compared to beryllium to magnesium, which one's bigger? Magnesium's bigger. And then calcium would be also bigger. And so this is the problem with beryllium. Beryllium is small. When it's small, it makes it more reactive. And so you have a +2 concentrated into a smaller volume. Electrically, it's going to be much more reactive. And what it does is it displaces things like magnesium and calcium. You need magnesium and calcium balance in your body. And if something comes in there and disrupts that, like beryllium, then it can screw up the biological function of these. And the same thing with strontium. You know, strontium can go in there. Strontium would be the next member of the family. And it would be even bigger or smaller than calcium? It'd be even bigger. Well, bigger means less reactive in this case, because in this case we're looking at concentrated charge. This is different than when we're looking at the metals. When we're looking at the neutral metals, the most reactive was which one? Cesium. Remember, we wanted to see the big explosion when cesium reacts with water. And so the most reactive one was cesium. But once we form what's called an ion, once it's lost an electron, then which of these ions would be the most reactive? The smallest one. The smallest one is going to have the largest electrical interaction. And so here, beryllium is going to be more reactive in any of these. Strontium, the concern there is there's radioactive isotope of strontium that's emitted in nuclear fusion type reactions. one concern with strontium is it can substitute calcium and magnesium in your bones. Which wouldn't be that big of a problem if it wasn't radioactive. But since it is radioactive, it's a problem. Okay, so strontium and then calcium, strontium, what's next? Barium. And so when we're thinking about things like reactivity, I usually think in terms of like concentration of charge. You know, all these are charged the same, but the volume, you know, is much more concentrated here than it is here. And same thing here. Beryllium 2+ would be highly concentrated positive charge here. Here it's a lot less concentrated. Meaning less reactive. Okay, now we have a couple of choices here. So for example, we can go from, let's go from magnesium to, there's a big gap here. So this is what I like to call A. This would be the A block here, and then there's a big jump. And then we resume the A block. Okay. And so if we're at beryllium, we jump over to boron, or if we're at magnesium, we jump out to aluminum. And so a lot of periodic tables will label, you know, aluminum and boron as being part of group 3A. Boron's a little bit tricky. So let's take a look at aluminum instead. What's the charge on the aluminum ion? It's going to be, what is it? 3+? Yeah. That's correct. And we just call it the aluminum ion. So all of these are just the name of the element, calcium, plus the word ion. The same thing with this, aluminum ion. These are what we call fixed charge. So we can get the charge off the periodic table, including, for example, after calcium, do you know what element this is here? After calcium comes scandium. And scandium is always, you know, the charge? 3+. It'd be smaller than calcium, but. And aluminum's always 3+ too. And so up to group 3, we have fixed charge. But when we go from scandium, what's after scandium? To the right, titanium. Now, losing 4 electrons starts to become very difficult. It's not an easy thing to do. And so, yes, this would like to go 4+, but who's going to take the electrons? It has to be something quite powerful. And sometimes we don't have things that are powerful enough. And so normally when we get to 3, okay, when I get to 4, I'm going to write like a Roman numeral here to indicate that. In fact, it's more likely that it's whatever comes in here to strip the electrons is going to have a harder time doing it. And so what we can end up with is titanium +1, or titanium 2+, or titanium 3+, and then maybe titanium 4+. Like that. But again, 4+ is getting high. It's not that it can't happen. There's usually something in addition. In other words, usually it's not monatomic. Monatomic, these are monatomic ions, meaning it's just one atom.
Does writing it as on the moment that it's not likely?
It means that it's a little bit more complicated than.
Is that why they use things like chrome or paint to like corrosion? Because it's so difficult to actually make it possible.
Coating with wood, chromium.
Yeah.
Chromium is really good. This is chrome plated, yeah. It's hard to oxidize. But titanium, and then we go to, after titanium comes what? Well, to the right. Vanadium. And vanadium is what, element number 15? 23? Element number 23? And how many electrons would it like to lose?
5.
5, yeah. And so here, I'll just write it in Roman numeral. You know, it's going to be hard to get it to 5. And so the typical charges that we see for vanadium are vanadium plus 1, vanadium 2 plus, vanadium 3 plus, vanadium 4 plus. 4, again, is hard. And so maybe 1, 2, and 3 are okay. And that's a pretty good compromise, maybe 2 and 3. And so these are what we call common charges, plus 2, plus 3. So we see, you know, it could lose up to 5 in the case of vanadium, or up to 4 in the case of titanium. But sometimes we don't see that. Sometimes we'll just see it lose 2, maybe 3 instead. And so these would be common charges. And the 5 would be max charge here. And so the Roman numeral is nice because it tells you, like, if you look at vanadium, what group is it in? 5. And so the max charge on vanadium is plus 5. Chromium, what group is chromium in? 6. So the maximum charge on chromium is plus 6. Do you think plus 6 is easy? No, it's hard. And so we usually use Roman numeral. So for example, if I say chromium 6, I usually say chromium Roman numeral 6, because it's going to be hard. It needs to be stabilized by something. And that's something that stabilizes it is usually oxygen. That stabilizes it. Manganese. What's the max charge on manganese?
7.
Yeah, plus 7. That's going to be especially difficult to get. Right? And so the most common charge for these species are plus 2, plus 3. Plus 2, plus 3 is not taking too many electrons. And so it's not going to be too much work to do. And so chromium plus 2, plus 3, manganese plus 2, plus 3, iron plus 2, plus 3, very common. In fact, plus 2, plus 3 is very common for variable charge all the way up to copper. What group is copper in? 1, yeah. So it drops down to 1 again. And so what do you expect the max charge for copper to be? It should be plus 1 if it's in group 1. But copper doesn't play by the rules exactly. And so what we have here is it's going to go vanadium, let's see, scandium, titanium, vanadium, what's next, chromium?
Yes.
And then what? Manganese, iron, cobalt, nickel,
Yes.
which are going to be group 8, to put a max of 8. But that's really hard. Plus 2, plus 3 is much more common for all these. And then copper, and then zinc. And so we're back to 1 and 2. Zinc plays by the rules. What should zinc be? 2 plus. And in fact, zinc is only 2 plus. Cadmium also plays by the rules. Cadmium is only
Plus 2.
2 plus. And silver plays by the rules. And silver will be plus 1. And so these 3 are fixed charge. So what we have is we have variable charge here. I mean, can you imagine losing 8 electrons? That's just not going to happen for iron. And so what we have is the common charges for this area of the periodic table is +2, +3. And so once we go past scandium, scandium's fixed charge. Scandium's always +3. But we go here, and what we're going to have is variable charge. The max charge is going to be given by the group number. And the common charge in this part of the periodic table will be +2, +3. So I could pick any element in there. Probably +2, +3 is it. The most common charges. Okay, when I get over here, then in this part of the periodic table, +1, +2 are the common charges here. So for example, copper, there are 2 copper ions, and the 2 copper ions are copper +1, which we'll just call copper plus, and copper +2, which we'll call 2 plus, like this. Whenever we have variable charge species, we have to name them differently. So to keep these separate, copper with the plus charge, we'll just call copper Roman numeral 1, all one word, no space. And then copper with the 2 plus charge, we'll call copper Roman numeral 2. And the same thing here. This would be titanium Roman numeral 1, titanium Roman numeral 2, titanium Roman numeral 3, and titanium Roman numeral 4. That's how we name those differently. And so whenever we have a variable charge, we have to include the Roman numeral in addition to the name. Except for these. Zinc is always +2, cadmium is always +2, and silver is always +1. Some of these are a little bit more tricky, like mercury. Mercury is below cadmium. Mercury you'd expect to be +2, and mercury +2 does indeed exist. But also mercury +1 exists, and mercury +1 is a very weird looking ion because it has 2 atoms of mercury, and the total charge is +2. So that means each mercury is +1. And so the first one up here, we call this one mercury Roman numeral 2 ion. And the bottom one here would be mercury Roman numeral 1 ion. And so those would be the 2 here. And then gold doesn't play by either of those rules. For gold, +1 and +3 are the most common for gold. And so gold 1, gold 3. Gold with a 3 plus charge is not stable. So it has to be stabilized by something. So that's why I wrote it in Roman numerals here. Okay, so most of the periodic table in this variable charge region is +2, +3, the metals. And then we have this, group 1, 2 here. This is going to be +1, +2 for the most part. And then tin and lead. Tin and lead, this is +2, +4 is the variable charge. Like carbon, carbon monoxide is +2, carbon dioxide is +4. Carbon's at the top of this family. And then things like arsenic, antimony, bismuth, these are +3, +5. Those are in group 5. And so losing a max of 5 electrons is tough. And so +3 is a compromise here. And then tin and lead are in group 4. Losing a max of 4 could be tough too. So +2 is a compromise there. And so for variable charges, usually we remember kind of the regions. So this is the region of +2, +3. This is the region of +1, +2. This family, the carbon family, is +2, +4, like carbon monoxide, and then the nitrogen family is +3, +5. For the charge. Now, for monatomics, some of these form monatomics, others don't. And so I told you getting +4 is tough. And so 10(2) is not a problem. So we have 10(2) plus like this, we call it 10 Roman numeral 2. But if we were to put a 4 plus charge, we might put 10 with a 4 plus charge like that, but getting that 4 plus could be difficult. So this is why I use the Roman numeral just as a kind of way to show, maybe the charge isn't exactly 4 plus. Losing that many electrons isn't make it so easy. Let's continue on. On the left side, it's easier to lose electrons. On the right side, it's easier to gain electrons. So let's keep going across the periodic table here. And then we'll get to carbon. Carbon's kind of in the middle. Do you see that? Carbon can either gain or lose 4 electrons. If carbon loses 4 electrons, that's hard to do, so I'm going to use Roman numeral here. We'll get carbon 4 plus. And so this one we just call the carbon 4, Roman numeral 4. Maybe not necessarily ion, because there's got to be something else helping stabilize that. Or the carbon with a 4 minus, if it gains 4. Carbon with 4 minus is not called carbon 4, it's called carbide. And so when we have the I ending, that just means it gains enough electrons to be like the nearest Nobel gas. Nitrogen, nitrogen again, it could go +5, like I wrote over here, plus Roman numeral 5, I should probably write. That could happen, or it's much more likely to gain. What will they gain in this case? 5? No, lose 5 or gain 3. So if it gains 3, it's going to be like that. If it loses 5, I'd write it like this. 5 plus with the Roman numeral. I'd call this nitrogen Roman numeral 5, but over here I call it not nitrogen Roman numeral 5, I'd call it, what would this be called? This would be called nitride. This would be nitrogen Roman numeral 5. Okay. Well, we aren't going to find, much nitrogen Roman numeral 5. We usually find nitrogen Roman numeral 5 in other things. Other things like the 8s we'll talk about. And actually, maybe I'll wait. It's stabilized. And normally, something has to take those electrons. And what takes electrons? Oxidizers take electrons. And the prototypical oxidizer is oxygen. And so a lot of minerals are these elements that have been oxidized to form minerals, like carbonate, as an example. In carbonate, we would have carbon in the +4 oxidation state. In nitrate, we'd have nitrogen in the +5 oxidation state. So usually the 8s refer to the completely oxidized mineral. So we had nitride, and then what? So nitrogen, then we have oxygen, which would give us oxide, and then fluorine, which would give us fluoride. And the max positive charge of fluorine would be plus Roman numeral 7. It's in group 7. Oxygen's in group 6. The max positive charge would be plus
has the potential to lose that many electrons?
It would never happen, but it has that potential to lose that many electrons. Apparently. You know, and what we're doing is we're doing bookkeeping with this.
When you say lose, do you mean like when it bonds to another like molecule, or do you mean like it leaves the base?
No, it bonds to another atom or atoms. So this is what I mean by lose. Here, carbon is not going to lose them in the form of standalone carbon plus 4 cation. When carbon loses it, it's going to get in a tug of war. It's going to get in a tug of war with something like oxygen. 3 oxygens come along and attack carbon. Tries to take all the electrons from it. The most electrons it can take from carbon will be 4 electrons. And then what we end up with is something like this. This is carbonate. Carbonate, if we give oxygen its preferred charge, what is the preferred charge on oxygen? Oxygen would like to gain 2. So if each oxygen gained 2, that's going to give me 2, 4, 6, a total of -6 over here. And then I have 1 carbon. So -6 plus what will equal the net charge? The net charge on this is -2. So carbon must be plus 4. And so this is what it means by apparent charge. The apparent charge is apparently carbon must be plus 4 if oxygen gets all the electrons it wants. The problem is that carbon is not going to give up the electrons so easily, and there's going to be a fight for electrons or a tug of war. And so even though, yes, if we bookkeep like this, then yeah, carbon would be plus 4. And it might not accurately be like that, but it's very useful for understanding some of the properties of carbonate. Anyway, so we have these. When we have the ides, we know the ides are typically monatomic anions with a D. These are monatomic anions. The charge you can get from its position on the periodic table. So for example, chloride. Chloride's in the same family here, so the charge would be -1. That would be chloride. And we know it's monatomic because of the I, unless, okay, it's monatomic anions except these ides. Do you know, did I give these to you last time? Or the ides that aren't monatomic? Bromide's monatomic. And the charge we can get because it's in the same family there. No, these except these polyatomic ides. There aren't that many. The polyatomic ides would be OH minus. You know what OH minus is called? Hydroxide. And so here's the difference. Normally when we do an ide like chloride, it's chlorine. Or fluoride, that's fluorine. Or oxide, that's oxygen. But is there an element like this, hydroxide? Is there like a hydronium element on the periodic table? No. And so this is different. So this has got to be polyatomic hydroxide. And so we just memorize these. The others we can get off the periodic table. Is there an element per oxonium? Because this would be peroxide here. And there isn't. So peroxide, we just memorize that. And then cyanide is another one that's common. This would be cyanide. And so these 3 we have to memorize. The others we can just get off the periodic table. And so if I'm thinking about the ides, I probably am only going to memorize 3 ides. Hydroxide, peroxide and cyanide. So all the other ides I should be able to figure out on the periodic table. So for example, if I'm looking for sulfide, what would the symbol for that be in the charge? Well, sulfide's got to be sulfur, which is S, and the charge 2 minus because it's in the oxygen family. So, the weird thing happens with the anions. You know, because of the negative charge, the anions get big. So normally fluorine's quite small, but fluoride, it's got an extra electron. Holding on to the extra electron means that it's more difficult. Therefore, the electron cloud is a bit bigger. We call this electron cloud, or bromide as well. We talk more about sizes later. This is just to get you thinking about it. Okay, those are the ides. Then we have some eights. Most of the eights we can get off the periodic table. Except for these eights. Did I give you a list of eights you just have to memorize? What are the eights that you just have to memorize? Okay, those you can get off the periodic table.
Did you say something about max oxidation state?
The max oxidation state will kind of help you figure it out.
Oxalate, acetate,
Yeah, oxalate.
dichromate.
Oxalate is C2O4, 2 minus. Normally when we have the 8s, it's maxed out. Oxalate. 8, historically, it's completely oxidized. And so in this case, what would the carbon be here? If oxygen got its preferred charge, oxygen likes to be 2 minus. If each oxygen were 2 minus, we have 4 of those. And that gives us a total -8. And then we have 2 carbons. 2 times X plus a -8 has to equal the net charge of -2. So what is X? 3. So if I do that, 2 times 3, that does it, huh? 2 times 3 is 6, -8 gives us -2. So both of these are 3. That's not maxed out. That's not maxed out, but it's just a rule. The rules can be violated. Historically or traditionally, the 8s have been thought to have been maxed out. So oxalate, what else do we have? This is a tough one to remember too. What's that one called?
I should have written down acetate.
Acetate, yeah. There are 2 ways of writing acetate. This is one, or alternatively, we could write it CH3COO minus. This is another way of writing acetate. And then we have this one. You know what that's called? Permanganate. Is this one maxed out? What is the max positive charge on manganese? 6? 7. So is this one maxed out? So I have 4 oxygens. It's going to give us -8, 1 manganese. So that's going to be plus something, and this has got to equal the net charge of -1. So,
7.
yeah, this has got to be manganese 7. Manganese, Roman numeral 7. Now, this is not monatomic ion. This is a polyatomic ion. And so this is how you can stabilize the +7. This +7 is stabilized by having all these oxygens gaining up on it, like this.
For the carbon one earlier, you used like the Roman numeral 3, even though that's not the max.
Yeah, it's not the max, but it's in this polyatomic species. So usually,
You read it.
well, carbon I do. Others I might not. Others I might. I know there's a lot. If you don't, if you do, or if you do, it's not. I'm not going to knock you, not points off you. So you're saying, yeah, 3+. It's like the same thing with gold. Now, gold, I probably don't write 3+ like this. Gold, I'll probably write the Roman numeral 3. And that's because I know a little bit more about gold and carbon than you probably do. So I don't expect you to necessarily know. Okay. What else do you have to memorize? So oxalate, acetate, permanganate. Were there some more? Yeah, let's look at chromate. CrO4 2-. It's chromate. You know, it's so easy to get the charges mixed up. I mean, this is 4 oxygens, that's 4 oxygens, that's -1, that's -2. But one thing that might help you is the oxidation state, the max positive charge here. So for chromate, we have 4 oxygens at -2. This is going to give us -8. And then 1 chromium. And so that chromium has got to be plus what? 6. That's got to be +6. +6 -8 is going to give us -2, the net charge here. And so this is what we call chromium 6. And we do Roman numeral. And so this is chromium 6. Did I mention? Have you ever heard of Aaron Brockovich?
I thought it was Rockovich.
Aaron Brockovich. Have you heard of Hinckley, California?
Yeah.
Hinckley, California. Apparently, they have a lot of chromium 6 contamination in the well. And it's not chromium 6, it was chromate contamination and one other one. In addition to chromate, you need to know dichromate. Dichromate seems to be like 2 chromates, but it isn't. It's almost 2 chromates. 1 oxygen is missing. And we have to lose one of the oxygens in order to link the 2 chromates together. We'll talk about it later. But this is also going to have a 2-. What's chromium here? Is that chromium 6 also? Or is that chromium something else? Chromium 6 is the max. Maybe this is less. Maybe it's chromium 5, chromium 4, chromium 3. What is it? And so we have 7 oxygens. We can just add those out. That's going to give us -14. 7 times -2. We have 2 chromiums. And this has got to equal -2. So 2 times x plus -14 is going to give us -2. So x must be 6. So this is also chromium 6. In fact, both of these are chromium 6. And so I think the well water in Hinckley, California was contaminated either with chromate or dichromate or both. The problem is that both of these are carcinogenic. And led to the movie being made. Okay, and any others that we have? Is that it? I think that was it. The other 8, fortunately, we can get off the periodic table, so we don't have to memorize it. But if you memorize these, then you can remember. Permanganate maxed out at manganese 7. Chromate, dichromate maxed out at +6. So if you accidentally, let's say, you put this as a -1. If you put this as a -1, what would chromium's charge be? Well, this has to add up to -1. Therefore, chromium's charge must be +7. Is +7 a reasonable charge for chromium? No, it's not. And so this way you can catch yourself. Or let's say you put 3 oxygens instead. You put 3 oxygens, would you get chromium 6? No. Not unless you had a much higher charge or much lower charge or something for the charge. And so sometimes that can help you out. Although oxalate didn't work so well, did it? But there are others that work well. And so off the periodic table, we start off with boron. What group is boron in? Group 3. 3B or 3A, depending on what periodic table you're looking at. And so what is borate? Well, we expect the max charge on boron to be +3. And so what is borate? BO2. And the charge on that?
-1.
Yeah, BO2 -1, that's reasonable. BO2 -1. But one easy way of remembering it is 333. 333, it's in group 3, and then boron has 3 oxygens with a 3- charge. That would be it. So this would be borate. It's maxed out. So 3 times -2 is -6. -6 plus 3 gives us -3. So this works out. Borate. So we just, actually, this one you don't even have to memorize. It's 333. And then carbonate's going to be what? We go to carbon. Carbonate is CO3. Charge?
-6.
Yeah. What's the oxidation state on carbon here? So we have 3 oxygens at -2, so that's -2 times 3 is -6. -6 plus what gives us -2? So it's got to be -6 plus 4 gives us -2. So do you see carbon's maxed out there? It's in group 4. So far it's working okay, carbonate. Okay, next to carbon is, so this is carbon 4, this is boron 3. Next is, what? Nitrate. Okay, what's the formula for nitrate? NO3 minus. Is this maxed out at +5? Is it? So oxygen's -2. -2 times 3 is -6. -6 plus what gives us -1? +5. So that's maxed out. So historically, these nitrates, these carbonates, these borates, these ones have been oxidized to the max. And these are the minerals that are found in nature. We live in an oxidizing atmosphere. There's no oxate, so we'll skip that. And then we'll go to chlorine.
I have a question.
Uh-huh.
What was the rule for we have the nitrate for the final charge, how it's -1?
Mm-hmm.
What's the rule for that?
The rule for figuring out the charge on nitrogen, or the rule for figuring out the charge here at the -1?
The -1.
The -1 is not a rule. The -1 is just a pattern. 3, 2, 1.
Oh,
This is what's observed in nature. So if somebody's analyzed nitrate and figured out it has a -1 charge from observation.
The way to also recognize it all the eights that are found up in the periodic table are always 3 oxygens.
Yeah. All these are 3 oxygens. That's good. So fluorate would be
FO3
FO3 and the charge? Minus. Here's where it kind of fails because fluorine's in group 7. So the max positive charge should be +7 here. But when we look at fluorine, is it +7? No, this would be fluorine, Roman numeral. Can you figure it out? So if oxygen's -2, -2 times 3 is -6. -6 plus what gives us -1? +5. -6 plus 5 gives us a. So this is not maxed out. But this is what was found in nature. Because it's hard to max out fluorine. I mean, does fluorine really want to lose 7 electrons? No. And so what had to happen was, in order to max this out, well, it's not quite there yet. And so they had to do something else. But before I do that, let's look. Below fluorine is chlorine. So what is chlorate? ClO3 minus. Bromate?
ClO3 minus.
Okay. With bromine, it would be BrO3. With iodine, it would be IO3 minus. Yeah. Fluorine is hard to max out at +7. It just doesn't want to lose electrons. Chlorine's a little bit better because chlorine's bigger. Chlorine being bigger, it's going to be easier to take electrons. Bromine will be a lot easier, and iodine would be the easiest. And so here, we'll start off with chlorine. So in order to max this out, well, they were wrong. Chlorate is wrong. They should have named ClO3 minus chlorate. You know what they should have named chlorate? They should have named ClO4 minus chlorate. This should have been chlorate, but it wasn't. You know why? This should have been chlorate because what would the positive charge on chlorine be? So if oxygen's -2, we have 4 of those. That's -2 times 4 is -8. -8 plus what gives us -1? 7. And so this is maxed out, but it's already too late because they named this chlorate. So the geologists probably, or mineralogists, named this one chlorate, the chlorate containing mineral, and then therefore they had to come up with a new name for this. What's the new name for this? Well, they call this one hyperchlorate, but hyper is too long, and so they'll shorten it to just perchlorate.
What does per come from?
Per means one, more extreme than chlorate. Just hyper. Hyper would be more. Hypo would be less. And so this is perchlorate because it just chlorate wasn't all the way there. How about pernitrate? Could I make a pernitrate?
No.
Why not? You're right. I wouldn't be able to make a pernitrate. Yeah, it's already maxed out. Nitrate's already maxed out of nitrogen 5. And so there's no way I'm going to take it farther than that, because that's the max. Here, it wasn't maxed out, but they called it chlorate. Well, that came from historical.
Observation, right?
Yeah, historical observations. They thought it was maxed out. It's just hard to make these. Something like perchlorate is, think about it, perchlorate's +7, chlorine's 7. Do you think chlorine's happy to lose 7 electrons? No.
What's the history behind the perchlorate synthesis?
Perchlorate's dangerous stuff. Although it's not like chromium-6. Chromium-6 was causing a whole bunch of cancer cases. Las Vegas had a huge problem with perchlorate in their water. There's a perchlorate factory. Have you ever heard of Pepcon? Pepcon's perchlorate factory just north of Las Vegas. And unfortunately, the perchlorates got into the drinking water, into the aquifer there for Vegas, and was contaminating the water. I don't know what kind of diseases led to or what ill health effects, but I do know that they got it out. They used a lot of, and it's not easy to get out, but they got it out. They got it down to acceptable levels so that people can drink the tap water in Vegas. You heard that? But I'd rather probably drink trace amounts of perchlorate than chromium 6, maybe. I'm not sure, or maybe chromium 6.
Is it hard to synthesize perchlorate?
No, not anymore. Not with with the synthetic methods that we use. But you have to be careful. If you synthesize perchlorate, you have to be careful because perchlorate is what we call a powerful oxidizer. And if you're dealing with a powerful oxidizer, you don't want fuels around. Fuels are things that can burn, with oxidizers.
You used to work with perchlorate, right?
Mm-hmm. Perchlorate. So you can take a look at this. See. Have the video here. Just a short video.
The chemicals exposed to intense heat finally reach the point of combustion. Ooh, that's going to be loud. The magnitude of that sound when it reached us was still extremely large for something that traveled over our mind. You can't tell me people got out of that. Oh, no. It's got to be hundreds. But the destruction has only just begun. Minutes later, two smaller explosions ripped through the desert. You could see people actually literally running through the desert, trying just to get away from that. 4 minutes after the initial blast, the fourth and largest explosion erupts from the factory. The explosion is so intense, the shockwave vaporizes a nearby factory and registers 3.5 on the Richter scale. It was just like a wall of water. And I remember it literally picked me up off my feet and never touched the ground. I think it literally picked me up and threw me at least 4 feet.
But they did. They did have quite a few videos about how they got the perchlorates out of the drinking water down to a more reasonable level. There's feds win 1.1 billion in the settlement to clean up perchlorate, etc. So perchlorate's a big issue in Las Vegas water.
What is perchlorate used for?
Rocket fuel. No, it's not fuel. It's the oxidizer. It's used as a solid oxidizer. And so, if you give it a fuel like ammonium is a fuel, and you mix it with perchlorate, then you have a rocket fuel, basically. So you use that. And so they were making rocket fuel at that point. Anyway,
It can't be a bipropellant oxidizer. It has to be solid Walker boosters, right? It has to be in the solid form.
yeah, in the solid form.
And they just eat through the tanks, right?
Not necessarily. Solids react slowly.
No, if it was in a bipropellant.
If it was molten, then it would probably eat through the tanks. Yeah. But something like this, to go from chlorate to perchlorate is going to take an extra step, right? To go from +5 to +7. So this is why they thought it maxed out at chlorate, but it really didn't max out, and so that's why they had to use this. This is kind of an ad hoc thing. After the fact, after they named it chlorate, oops, there's one higher. We'll call it per. There's no such thing. You aren't going to have percarbonate, perborate, pernitrate. Those aren't going to happen because those are maxed out. So perchlorate. But even taking 5 from chlorine is tough. So chlorate is also a pretty good oxidizer. It really wants electrons because chlorine +5 is pretty high. And so what we can have are variations of this. So perchlorate's one more. Then we could have something like this, ClO2 minus. ClO2 minus would be called what? Chlorite. And so this is becoming more stable. Chlorine here, if this is -2 for oxygen, that's -4. Chlorine would be +3 here. So it's more reasonable. Or there's even one more. Do you know what the other one is? ClO minus. ClO1 minus is called, chloride is Cl minus. So chloride would be this. So we're on the positive end of the spectrum, and this would be called hypochlorite. So we have these two prefixes, hypo and hyper, but hyper's been shortened. Hyper means above, hypo means below. So we have those. So sometimes, we're going to have more, variety because maxing out's not so easy sometimes. Sometimes we'll come way short of maxing out. Okay, so borate, we remember that 333. We remember another one, 444. You know which one 444 refers to? 444. 333 is borate. 444 is.
Carbonate?
Not carbonate. Carbonate is not 444, but close. It's in the same family. The geologist would know this one because, carbonates are very common, and one other one is very common on Earth, rocks and minerals. Silicates, like granites and that kind of stuff. So 444, what do I mean by that? I mean group 4, silicon's in group 4, and it has how many oxygens? No. 4 oxygens in the charge? So this is silicate. Silicate is in a different pattern. And so if we remember silicate, 444, and borate, 333, the borate pattern forms this little elbow here. The silicate pattern forms this inner block. And so next to silicate is what? Phosphorus. And so what would phosphate be? How many oxygens and charge? What's the charge? Yeah. So phosphate would be PO43 minus. We just know that from the pattern. And the next to phosphorus on the right would be sulfur. So what would sulfate be? How many oxygens and charge? SO4 Yeah, SO4 2 minus. And so these all have 4 oxygens and the charge drops 432. But there's more to this pattern than this. So for example, below phosphorus is arsenic. What is arsenate? Arsenate is actually ASO4, and the charge 3 minus. So it stays the same like these. Chlorate, bromate, iodate is the same. And below sulfur is selenium, and so selenate would be SeO4, 2 minus, yeah, etc. Now these are all maxed out. So for example, here, silicon, that's 4 times minus 2 is minus 8. Minus 8 plus 4 will give us minus 4. So that's plus 4 maxed out. Phosphate's maxed out too. 4 times minus 2 is minus 8. Minus 8 plus 5 will give us minus 3. Same thing with arsenic. And sulfur is maxed out here. 4 times minus 2 is minus 8. Minus 8 plus 6 will give us minus 2. So there's no per phosphate, there's no per sulfate. We're topped out at the 8. So these, hopefully you don't have to memorize. You just have to remember 333 and 444. Remember those, and you should be able to figure out the rest of the pattern. Okay, let's take a look at naming acids and acid anions. Did I talk about that already? Okay. So I can get all these, and then, well, before I do that, I should probably talk about the ites. The ites have one less oxygen, same charge. And then we have the per-8 and the hypo-ite. The per-8s have one more oxygen than the 8s, same charge. And the hypo-ites have one less oxygen than the ites. Same charge. So we can figure out a lot of ions based on these patterns here. But we can figure out even more if we consider acid anions. Acid just begins with H, the element H. If it has a charge, we call it an acid anion. If it has no charge, we call it an acid. So we'll look at acid anions and acids. So if I have carbonate, CO3 2 minus, and I add an H plus to it, H plus is called acid, then I'll form the acid anion, HCO3 minus. This is an acid anion. It's an acid because it begins with the H, and it's an anion because it has a negative charge. And therefore, we just call it an acid anion, and then we would name this. The name of this is just hydrogen carbonate, 2 words, or bicarbonate, 1 word. Bicarbonate is by far the more common name for it, this acid anion. If I try to add another H plus, then what I form is an acid, not an acid anion. So if I try to add another H plus, I'm going to get H2CO3. And that negative charge is going to be canceled out by this positive charge here, and this is going to be neutral. Acids are not going to have any charge. They're going to be neutral. this. And we have a different naming system for acids. And it's based on the ending of the anion. So if the anion ends in 8, then the acid is just going to be the name of the anion, the name of the ion with the ate acid ending. So this is called carbonic acid. Do another example here. ClO4 minus. ClO4 minus is that chlorate? Is it chlorite? What is it? And so what I do is I look at the periodic table and then try to figure out what is chlorate, looking at the periodic table. And so chlorate would be ClO3 charge minus. And so this is ClO4, has one more oxygen, same charge, so it's got to be perchlorate. And so again, we have the 8 ending here. And that means, in this case, we can only attach one H+. We're not going to form an acid anion here. It's just going to go straight to an acid. Now, we always write the H first in acids and acid anions. So this is going to be HClO4, even though let's flip it over there. And so if that's perchlorate, then what's the acid name? Well, all we do is we drop the 8 and replace it with ic acid. Ic acid here. So we're going to drop the 8 and replace it with ic acid. So this is going to be called perchloric acid. Perchloric acid. If you look at the acid chart up there on the wall, do you see the one on the top left? What acid is at the top left there? Perchloric acid. Perchloric acid is the strongest acid on the acid chart. So this is very well known. All right, that's if it ends in 8. The other scenario is if it ends in ite. So let's take a look at some that end in ite. So carbonite, no, but chlorite, yes. Let's try chlorite or sulfite. What would chlorite be? Chlorate is ClO3, so chlorite's going to be ClO2, same charge, minus. And then we add an H+, and we get HClO2. So the anion is chlorite. If the anion ends in ite, then what we do for the acid is we replace the ending by aus acid rather than ic acid. And so chlorite gets changed to chlorous acid. And so HClO2 is known as chlorous acid. What's sulfate? Can you look at sulfate on the periodic table? What's the formula for sulfate in the charge?
SO4 2
SO4. Therefore, sulfite would be SO3 2 minus. So if we have SO3 2 minus, then if we add one H+, that doesn't quite neutralize the -2 charge. And that's going to form HSO3 with the -1 charge. This one is called hydrogen sulfide. Or bisulfite ion. Hydrogen sulfide or bisulfite ion. Now, if I add another H+ to this, then that's going to cancel out the negative charge. I'm going to get H2SO3. I'll need 2 hydrogens, balance out the charge. What's this called? So that depends on the anion name. So if we go back here and look at the anion ends in ite. And so what do? I change the ending. And so I change the ending to sulfos acid, but sulfurous acid sounds a bit funny, so they changed it. Rather than calling it sulfurous acid, they called it sulfuric acid. Sulfurous acid. Sulfuric acid would be sulfate going to ic acid, so that would be SO4, H2SO4. Sulfurous acid would be H2SO3. Sulfite going to the acid. The last type of anion we have is the ones that end in "ide." If we have an "ide," then we switch the name. This one's a little bit more complicated. We add the hydro prefix and the ic acid suffix. So what's the name of this ion? Cn minus. Cyanide. So if we have cyanide and we add an H plus to this, then it's going to balance out. We're not going to form an acid anion, we're just going to form an acid. This is the acid here. What's the name of the acid? So what we have to do is, it's an ide with a D. So we have to add the hydro prefix, so it would be hydrocyanide, but we drop the ide and replace it with ic acid. So hydrocyanic acid. So hydro gets added on and the ic acid gets added on. What are their ides? This is a polyatomic ide. Most ides are monatomic, like this. What's this called? This is Sol 5. And so if we have an H plus to this, then we're going to make HS minus. What do you call HS minus? Is that an acid or acid anion? That's an acid anion. It begins with an H and it has a charge. Acid anion.
Acids don't have a charge, right?
Yeah. I mean, at least at this level, they don't have a charge. Later on, let's see, we'll broaden the definition of the acid. It's just getting the nomenclature down first. Okay, so something like this, what do we call that? We could call this hydrogen sulfide, but in this case, we have to call it hydrogen sulfide ion. There's some additional complications that come up. Or bisulfide. The reason is because there are different ways to name acids. And so if we add another H plus to this, then we're going to form the acid. And the acid is going to be H2S. H2S, well, we have an ide. If we have an ide, then that means we need the hydro prefix. It would be hydro, and then sulfur would be sulfic, but it sounds funny, so we'll go with sulfuric. Hydrosulfuric acid. That would be the name of this as an acid. But there's a common name for this. The common name for this is just called hydrogen sulfide. And hydrogen sulfide, a lot of people know hydrogen sulfide because it's the Rotnego gas. This stings. And it's also toxic. So hydrogen sulfide. Hydrogen sulfide, we're naming it as an ionic compound. If we were to follow our normal binary or nomenclature rules, we call it dihydrogen monosulfide. So we don't do that in this case.
Why do we have to add the hydrogen sulfide ion for like the ides and not for the ites and ates?
The ion?
Yeah.
Because the common name for this is hydrogen sulfide. And it's just because people call this hydrogen sulfide.
Is
So
it for sulfide specifically then? Or for all of the ions?
that we add ion.
Yeah.
This one specifically, pretty much. This one and the analogous ones like hydrogen selenide, etc. The reason is this. You know, ionic compounds are named based on the cation and the anion. So the cation here is the hydrogen ion, and the anion is cyanide. And so the ionic name for this would be just hydrogen cyanide. Hydrogen cyanide is a gas. And if I take this hydrogen cyanide gas and mix it with water, I'll form hydrocyanic acid. Hydrogen sulfide is a gas. Hydrogen sulfide smells like rotten eggs. Hydrogen cyanide smells like burnt almonds. But both of these are gases. So oftentimes we'll have multiple names for the same thing. The same thing happens with this. What is the name of this? Hydrogen chloride, is it? Hydrogen chloride, we can get pure hydrogen chloride, and we mix it with water, we'll form what acid? Yeah, or hydrochloric acid. There's some clues that tell you which one is preferred name. We can get to, we'll take a look at that in just a minute. We'll go on a break right now. I have to leave early. All right, when I say ionic compound here, I mean ionic compound rules. Rules for ionic compounds is we never write the numeric prefix. So, for example, we would never call this dihydrogen monosulfide. Do you know why? The reason why is because we could figure out how many H pluses we need to neutralize this. Sulfide's a 2 minus, we need 2 H pluses, so it's got to be H2S. And so for these, we use the ionic compound rules. In ionic compounds, we can figure out the charges, and then we can figure out the ratios in order to get electrical neutrality, which we have to have here. The rules for molecular compounds are binary. Non-metallic compounds is a little bit different here. So blue is usually reserved for nitrogen. And so this is N2, which would just be elemental nitrogen. What would this be? This would be N, and oxygen would be red, so it would be NO2. NO2 is called nitrogen oxide or nitrogen dioxide. It's dioxide, and the reason is because nitrogen can have a variety of charges all the way up to plus 5, and it's hard to get to plus 5. You might stop at plus 4. Nitrogen dioxide is -2 -2 plus 4. This one, do you know what this is? This is another nitrogen oxide, except this one is N2O. N2O is called dinitrogen monoxide. Or these have common names. NO2 is called nitric oxide. N2O is called nitrous oxide. Those are common names. This one over here is N2O4. And this would be dinitrogen tetroxide. And so something like this with a variable charge, it's hard to figure out, but something like this with a fixed charge, we can easily figure out the ratio. Even if it's variable charge, as long as we're told what the charge is, then we can figure it out. And that's not a problem there. Actually, I just saw a video on some more stuff on nitric oxide and hair. But let's go over here. The yellow is going to be fluorine, the green is going to be chlorine. So this is F2. F2 is elemental fluorine. It's diatomic. Now, what should we call this? Should we call this chlorine monofluoride or fluorine monochloride? Who should get the "ide" ending, the IDE ending? Normally, when we think about the "ide" ending, the person that gets the "ide" ending, the element that gets it, do they take the electrons or do they give up the electrons? They take. And so, which element wants the electrons more, fluorine or chlorine? Fluorine or chlorine? Chlorine? Well, in this case, the smaller sized atom is going to be the more reactive. And when we look at this, which one's smaller, fluorine or chlorine? Fluorine's more smaller, therefore more reactive. And so this is going to be called chlorine monofluoride. That means fluorine is going to be taking the electrons. Both of them want to take the electrons. Both of them are oxidizers, but in this case, one of them has to be the loser, the other has to be the winner. And when it boils down to is fluorine's going to be the winner. How about this one over here? This would be chlorine trifluoride, and this last one would be chlorine pentafluoride. That's it. Okay, so we use the prefixes when we don't know what the ratio is going to be. But in something like this, CaCl2, would we call that calcium dichloride or calcium chloride? You would think you call it dichloride, but here, calcium's fixed charge. What is the charge on calcium? 2+, and therefore we have to have 2 chlorides. So saying dichloride, it's not necessary because we can figure out how many chlorides need to attach to the calcium. And so this one would follow the rules for ionic compounds and just be called calcium chloride. If I had aluminum, aluminum has a charge of what? 3+. How many chlorides would I need to attach to aluminum? 3. And so should I call it aluminum trichloride or just aluminum chloride? Yeah, we're just going to call it aluminum chloride because we know aluminum's 3+ and we need 3 chlorides on there to do it. Now, it could be a variable charge, but we need to know what the charge is. So, for example, if we say iron, then I don't know. Iron, what are the most common charges on iron? Is it in the +2 +3, the +1 +2, the +2 +4, or the +3 +5 region of the periodic table? +2 +3. So we know iron likes +2 or +3, so we need to know which one it is. So for example, if it's iron 3, then we know it's going to have what? 3 chlorides. So if we had this, we would call it FeCl3, and the name for this would be iron Roman numeral 3, because we need to know that's iron 3, not iron 2. Iron 3 trichloride or iron 3 chloride? It would be iron 3 chloride, because once we know it's iron 3, we know we need 3 chlorides for that. Whereas over here, if I have nitrogen, how many oxygens do I put on there? Do I really know that for sure? No, I would need to know the oxidation state of nitrogen in order to figure that out. Okay, so let's get some practice here with this. sulfuric acid. Ic acid means what? If you see, there's no hydro. If it were hydroic acid, that's something. But this is just ic acid. There's only three. There's ic acid, aus acid, and hydroic acid. So if I have an ic acid, what's the anion? Ate, ite, or ide? Ate. So this would be, sulfuric acid would be sulfate, right? And sulfate is what? SO4 2 minus. And if I know it's SO4 2 minus, how many hydrogens do I need? Two. So it's going to be H2SO4. So sulfuric acid is H2SO4. There are three big acids that you definitely need to know. One of them is sulfuric acid. Very common. You know what the other two are? Hydrochloric acid and one more. No. Hydrofluoric acid. Nitric acid, yeah. Those are the three big ones. Acetic is also up there as well. Or strong acid. Okay, so that's ic acid. This, you see there's no hydro here. It's just ic acid. So this must be chlorate, chlorite, or chloride? Chlorate. It's going to be chlorate. Can you look at the periodic table and tell me what the formula for chlorate is? Three oxygens or four oxygens? Three. ClO3 and the charge? Minus. So this is chlorate, and so chloric acid would be HClO3. That would be chloric acid. So this is, there's no hydro, so this is ic acid. So let's either bromate, or bromide. This is bromate. And so if we know chlorate, then we already know bromate. What's bromate? BrO3 minus. And hydro, it's not hydro, it's just bromic acid is HBrO3. It would be bromic acid. Arsenic acid, it's ic acid, no hydro. So that's arsenate, arsenite, or arsenide. Arsenate. And so what is the formula for arsenate? So we got to look what's nearby arsenic. Yeah, in the same family as phosphorus, and phosphate was what? 40, back up more, 444. So arsenate is 8. It's a T. Whenever we have a T, it's going to be polyatomic oxyanion. So T in 8 and T in ite, polyatomic oxyanion. So we got oxy there, oxygen. How many do we need? 4. And the charge? 3 minus. And therefore, how many hydrogens do I need? 3. And so H3ASO4. This would be arsenic acid. Telluric acid. Telluric acid, would that be tellurate, tellurite, or telluride? Tellurate. And so you got to figure out what tellurate is. The tellurium is in the same family as sulfur and selenium. So what would tellurate be? TeO2 TeO4 2 minus? Yeah. That's correct. And so telluric acid would be H2TeO4. Telluric acid. Now this is different. This is hydroic. So when we have the hydroic, that's an ide. And so this is not bromate, this is not bromite, this is bromide. Hydroic, bromide. And so what is the formula for bromide? Bromide is, when you have a D, like bromide, D, that means it's usually monatomic. So this would be the element bromine. What's the charge on bromine? So look at the periodic table on -1. This one's one more electron. And so hydrobromic acid is, we just need one hydrogen. This would be hydrobromic acid. Take a look at the number 3 acid up there. Do you see it? HBr, hydrobromic acid. All right, let's continue on here. H2CO3, what's the anion name there? Is that carbonate or carbonite? Percarbonate? Hypocarbonite? Carbonate. And so if it's A, then what do we do the ending? Ic acid. So this would be called carbonic acid. Carbonate goes to carbonic acid. How about this one? This is
Hydrofluoric?
fluoride, which would go to hydrofluoric acid. This is sulfate or sulfite. Sulfate is what? SO4. Yeah. So this is going to be sulfite. So if it's ITE, then we get rid of it. So it should be sulfous acid or sulfurous acid. So H2SO3, sulfurous acid. IO4 minus. What would that be? IO4. Is that iodate? What is iodate? Yeah, IO3, and this is IO4, so we call this hyper or periodate. And so IO4 minus is periodate. If it's periodate, then what's the name of the acid? Well, 8, we just get rid of the 8 and then the periodic acid would be HiO4. Periodic acid. Is that tellurate or tellurite? Tellurate? Take a look at the periodic table. Tellurite. Tellurite is 4 oxygens. It's in the inner block and it's 4. So this is tellurite, which means this is going to be called tellurous acid. Tellurous acid. Is that bromate or bromite? Or neither? BRO. Bromite? What is bromate? So take a look at the periodic table. Bromate is how many oxygen? Bromate is 3. 3 oxygens. Bromite would be 2 oxygens, and therefore this must be hypobromite. If it's hypobromite, then it gives us what acid? It's called hypobromite. So what we do is we get rid of the ite and replace it with House acid. So it would be hypobromous acid. HBRO. Hypobromous acid. How about this one? HBRO4. Is that bromate?
Yeah.
Perbromate. It's perbromate. If it's perbromate, it's going to be called perbromic acid. Perbromic acid. So those are some acids. There are more here. Actually, I'll have to talk about the other stuff later. Unfortunately, I tried to reschedule this, but I couldn't find another time. So what we're going to do is we're going to do this. I forgot to publish this. I put the original nomenclature one on YouTube here, but I just published it now. Can you guys work on this? Where did I put that? If you go to modules, so you'll be able to get this off Canvas. Try to write the formulas for these or the names. Some of these are just straight memorization, so it'll probably take you longer, but some of these you should be able to get off the periodic table. So carbide periodic table, oxide periodic table, cyanide memorization, peroxide memorization, carbonate periodic table, fluoride periodic table, silicate periodic table, sulfide periodic table, dichromate memorization, chloride periodic table, perchlorate periodic table, silver periodic table, nitride periodic table. So most of these are off the periodic table. You shouldn't have to memorize them. So try these out, and then I have to turn this off. So maybe you can work with other people. If you can just bring it up on your phone or something. Okay?
I have a question. As far as for the exam coming up, so like the 24th or 21st?
The 25th.
The 25th. What's it called? Is there gonna be a study guide?
Right here.